called Stolz Theorem, okay, again, because of a mathematician called Stolz. So let a sub n and b sub n be two sequences of real numbers, and suppose that b sub n is strictly monotonic, increasing or decreasing. Okay, so it's either growing to yes, growing or decreasing. So it's either the limit of b sub n is plus or minus infinity, so it's either a divergent sequence. So for instance, if you think about, b sub n could be n or n squared, something like that. Okay? Or that the limit of a sub n and b sub n is 0, so then you would have a 0 over 0 indetermination, right? Then, and this is the important result, the limit of the quotient between these two sequences, a sub n and b sub n, is the same as this limit. The limit of a sub n minus a sub n minus 1 over b sub n minus b sub n minus 1. Okay, that's only when the latter limit exists. Okay, so if you were to apply this theorem and then you compute this limit, and this limit is not something that exists, then you couldn't apply this result. Okay? But in most cases, and we will have in the course, when you apply this, you will get to a number, okay, or something that you can resolve. Okay. So remember this. We will use this a lot, but with this result, we can now prove 3 corollaries, okay, that we will see now. So these are corollary. So what's a corollary? Corollary is another proposition, okay, so it's a proposition, but it's usually something that's easy to prove once you have a previous result, okay. So in this case, once you have Stolz theorem, this is super easy to prove, and I'm going to show you to you. Okay, so the proof for this is, so the corollary is that the limit of the sequence c sub n goes to c. Then this implies that the limit of 1 over n times c sub 1 plus c sub 2 plus whatever plus c sub n equals c. Okay, so if the limit of the sequence c sub n is c, so if this limit exists, then the limit of this kind of average, okay, this sum is the same as the original sequence. Okay, how do we prove this? Okay, so if we name this sequence c sub 1 plus c sub 2 plus blah 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 plus c sub n, this is a new sequence, right? So for instance, a sub 1 is c sub 1, a sub 2 is c sub 1 plus c sub 2, a sub 3 is c sub 1 plus c sub 2 plus c sub 3, and so on, right? So it is a new sequence. And we call b sub n n. Well, it's obvious that this limit is 1 over n times c sub 1 plus c sub 2 plus blah 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 plus c sub n. It's the same as the limit when n goes to infinity of a sub n over b sub n, right? So those things are the same. We're just calling them different things, right? Now, b sub n is a sequence that's monotonically increasing strictly, and it goes to infinity. So we can apply Stolz theorem and say this is equal to this limit, a sub n minus a sub n minus 1 over b sub n minus b sub n minus 1, right? Now, what's a sub n minus a sub n minus 1? If you think about it for a second, this is c sub n, right? And b sub n is n, and b sub n minus 1 is n minus 1. So this is just 1, right? n minus 1 is 1. So this is the limit when n goes to infinity of c sub n, which is c. So this proves the result. Okay? Okay, so next corollary. It's the same thing. The limit when n goes to infinity of c sub n equals c implies that the limit of the nth root of this product, c sub 1 times c sub 2 times blah 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 times c sub n equals c. Okay? So the proof is very simple. It's very similar to the previous one. If we take the logarithm, okay, so we say the logarithm of the nth root of c sub 1 times c sub 2 times blah blah times c sub n is 1 over n, and then the logarithm of c sub 1 plus the logarithm of c sub 2 plus blah 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 plus the logarithm of c sub n, right? So now the limit of the logarithm of c sub n is the logarithm of c, okay, we know that. Then we can apply this result. The limit of the logarithm of this c sub 1, c sub 2, blah, 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 c sub n is the limit when n goes to infinity of 1 over n of this sum, log, as we have just written, right? Plus the logarithm of c over n. But now this, we can apply the previous result, right? If we have our previous sequence, now it's the logarithm of c sub n, it has a limit, it's the logarithm of c. So this limit is logarithm of c, right? So the limit of this is logarithm of c. So the limit of this is c, okay? Because the logarithm is an injective function, right? Okay, so how do we apply this in practice? Well, normally you will have limits of this type, okay? So you say product of something in an nth root, and then you say, well, I don't know how to compute this, but I know that the limit of this is going to be the limit of c sub n. So if the limit of c sub n exists and is c, then you know that this limit is c, okay? So let me say that again, just in case it wasn't clear enough. Normally you will have this kind of limit, okay, which is kind of complicated, and you won't know how to compute the limit of this, okay? So the nth root of some product here, okay? Well, if you can make some transformations and algebraic transformations to this, so that you can see that there's a sequence such like this, and this sequence has a limit like this, then you can know that the limit of this is c, okay? Finally, have the last corollary to Stolz theorem. We have the limit when n goes to infinity of the quotient between a sub n and a sub n minus 1 is a. Then this implies that the limit of the nth root of a sub n equals a, okay? And again, this is easy to prove. So suppose we write this. A sub n is just a sub n divided by a sub n minus 1 times a sub n minus 1 divided by a sub n minus 2 times a sub n minus 2 divided by a sub n minus 3 times blah 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 times a sub 2 divided by a sub 1 times a sub 1, right? So this is the same thing, because we are multiplying and dividing by the same thing all the time, okay? So we can define now c sub n as a sub n divided by a sub n minus 1, right? For n greater than 1 and c sub 1 equals a sub 1, right? So then we have a sub n substituting here, we have c sub n times c sub n minus 1 times c sub n minus 2 times blah 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 times c2 times c1, right? So we can rewrite a sub n as a product of things. So now we have the limit when n goes to infinity of the nth root of a sub n. Well, this is the same as the limit when n goes to infinity of the nth root of c sub 1 times c sub 2 times c sub 3 times blah 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 times c sub n, right? But we have seen, this is the previous case, the previous corollary. We know that this is the same as the limit of c sub n, right? But the limit of c sub n is just a sub n divided by a sub n minus 1, okay? So if the limit of a sub n over a sub n minus 1 is a, this is just a, which completes the proof.